Welcome back to Day 9 of the 90-Day AI Mastery course. Today, we are going to explore classic number theory challenges in computer science. These exercises are highly popular in programming interviews because they test your ability to translate math rules into highly optimized loops. We will cover the logic and code for 4 iconic number types: prime, Armstrong, perfect, and strong numbers. Along the way, you will discover how simple math principles can optimize loops to run thousands of times faster. Let's get started. Let's begin with prime numbers. A number is prime if it has no positive divisors other than 1 and itself. The simplest approach is checking division for every number from 2 up to n-1. However, mathematically, if a number has a divisor, it must have at least one factor less than or equal to its square root. By ending our search at the square root of n, we can drastically reduce the number of operations. For checking if a large number like 1 billion is prime, this square root trial division reduces the iterations from 1 billion down to just 31,000. Let's see the Python implementation. Here is our optimized prime checker in Python. We define the function is_prime taking an integer n. First, we handle the boundary case. If n is less than or equal to 1, it is not prime. Next, we run a for loop starting at 2 and ending at the integer square root of n plus 1. In Python, we compute the square root using n***.5, cast it to an integer, and add 1 to make the range inclusive. If n is divisible by any value of I within this range, we immediately return false. If the loop completes without finding a divisor, we return true. This trial division loop is highly efficient. Next, let's examine Armstrong numbers, also known as narcissistic numbers. A number is an Armstrong number if the sum of its digits, each raised to the power of the total number of digits, equals the original number. For example, the number 153 has 3 digits. If we take 1 cubed, plus 5 cubed, plus 3 cubed, we get exactly 153. Similarly, the 4-digit number 1634 equals 1 raised to the 4th, plus 6 to the 4th, plus 3 to the 4th, plus 4 to the 4th. Let's implement a loop to check this. Here is the Python implementation for checking if a number is an Armstrong number. We find the power by counting the digits. Then we initialize a total sum to 0 and copy our number to a temporary variable temp. Using a while loop, we dissect temp digit by digit. In each step, temp modulo 10 extracts the last digit, which we raise to our power and add to total. We then prune the last digit from temp using floor division by 10. Finally, we check if our accumulated total equals the original number. Testing this with 153 yields true. Now, let's explore perfect numbers. A perfect number is a positive integer that is equal to the sum of its proper divisors, meaning all its positive divisors excluding the number itself. The smallest perfect number is 6, because its proper divisors are 1, 2, and 3, and their sum is 6. The next perfect number is 28, whose proper divisors are 1, 2, 4, 7, and 14, summing up exactly to 28. To write an optimized perfect number checker, we can check for divisor pairs up to the square root of n, just like we did with prime numbers. Here is the optimized perfect checker. If a divisor I is found, we add both I and its paired divisor n floor division I to our running sum, making sure not to add the square root twice if n is a perfect square. We initialize our divisor sum to 1, since 1 is a proper divisor of any number greater than 1, and start our loop from 2. Finally, we return whether the sum matches the original number. Testing 28 returns true. This approach runs in square root time complexity, making it extremely fast. Our final algorithm checks for strong numbers. A strong number is an integer where the sum of the factorials of its digits equals the original number. 145 is a strong number because 1 factorial plus 4 factorial plus 5 factorial equals 145. To optimize this checker, we should avoid calculating the factorial of each digit from scratch, which would require a nested loop. Instead, Since digits are always between 0 and 9, we pre-calculate their factorials in a lookup list named fact. Our loop then extracts each digit using modulo 10 and performs a constant time list lookup. This memoization technique converts nested calculations into instant lookups. What an amazing journey through classic number algorithms. Let's summarize the key takeaways. First, prime number verification is optimized by checking factors only up to the square root of n. Second, Armstrong numbers sum digits raised to the power of the length. Third, perfect numbers can be validated in square root time by adding divisor pairs. Fourth, strong numbers are verified efficiently using a pre-computed lookup table for digit factorials. Tomorrow, on day 10, we will dive into pattern programming, learning how to build pyramids and visual grids using nested loops. Thanks for watching. Make sure to like and subscribe, and we'll see you tomorrow.